Okay, so let's take a look at this. We are adding sterile water, which is basically just a neutral solution with no medical value, no medicine in it, to an 18% solution. So what 2% are we combining here? What 2% are we mixing? Obviously we have the 18%, but what's our other percent we're mixing with it? Well, we're trying to get 15 is what our result is going to be. But the sterile water has what percent medication in it? 0. There we go. So we're mixing 18% with 0% to create 15%. The amount of each that we have, well, we're told that we have 120 milliliters. That goes with which one? That is 120 milliliters of the 18%, so that's going to go with the 18%. We're asked to find the 0%, so we're going to let that be x. How much of the 15% are we going to create then? What's this volume going to be? There we go, 120 plus x. We could have done x plus 120 would work as well. So now it's just a matter of setting up the equation. Concentration times volume. 18% is 0.18 times 120 is the volume. 0%, let's see you later, Brett. 0% is 0 times x, so that's obviously going to be 0 and cancel out. Then 15% is 0.15 times 120 plus x. So the 0x cancels out. 0.18 times 120 is 21.6, I believe. 0x is gone. The 0.15 times 120 is going to be 18. 0.15 times x is 0.15x. And now we're going to solve. What's our next step going to be? Subtract the 18. So we got 3.6 equals 0.15x. And finally, divide by 0.15. So x equals 3.6 divided by 0.15 is 24 milliliters. Then we have to make sure we answer our question. X is 24 milliliters. That is the amount of 0% or water, which is what we are asked to find. So 24 milliliters is our answer. Okay, I realize I spent a good solid 2 days on those mixture problems, but those tend to be the more difficult ones for students to do. So hopefully they're going okay for you. We're going to move on today to one of the most powerful concepts in math, which is ratio and proportion. Today we're going to talk about ratios. Ratios are all about relationships. And the basest form, the basic structure of a ratio is just a comparison between two numbers. So all the ratio does is compare two numbers. So for example, I might look at students that are taking this class. Right now, I believe I have 18 total students taking it online or over the network. We'll just say ITV. I have 18 students. I have 12 students taking it in the classroom. So we'll compare it ITV to classroom. So that's an 18 to 12 ratio. And I can write it exactly like that as a fraction, 18 over 12. Or we can write it with a colon in it, 18 to 12. Or we can write the 18 to 12 like that. And I prefer to write it in this fraction form just because in that form there are a lot of things we can do with it that are similar to what we can do with fractions. For example, 18 and 12 can both be divided by 6. So I can divide out the 6 and get a 3:2 ratio. I could do that in any of these other forms. I mean, I could divide both of these by 6 and get 3:2 in that form as well. It's just I'm used to doing it with fractions. Now, one thing I have to be careful of, you'll notice I left this as 3/2. If this were a fraction, most cases we'd want to convert that to 1 1/2. But when we have a ratio, we never want to convert it into a mixed number. We always want to keep it as an improper fraction when it's a ratio. Because a ratio, remember, is comparing the two numbers. So it's not about the value, it's the comparison between the two numbers. I want to say just a little bit about this right here, 18 to 12. What that implies when you use that notation, 18 to 12, it implies that we are comparing two parts of a whole. We're comparing part A to part B. Now, I only have the two sections of this class. I have the ITV section that we're doing now, and I have the classroom section that I mentioned. So those are the two parts that make up the whole. But I could have done ITV compared to total students in the class. If I would have done that, of course, there'd be 18 students on ITV still, the 18. Now, total students, I have 18 ITV and 12 in the classroom, would have been 30. So that would have been 18 to 30. The wording I would have used there, though, would not be 18 to 30, as I just said. It would be 18 out of 30. So when I use that 18 out of 30, it tells me I'm no longer comparing one part of the whole population to a second part. I'm comparing one part, we'll call that part A, to the whole group. So now I'd still reduce this. Both can be divided by 6. Gives me 3 out of 5. So that is saying is 3 out of 5 of my students in this course are on the ITV network. So within a lot of these ratios, there are actually several ratios that are implied. And that shows here from my 18 to 12 or 3:2 ratio, I could get the 3 out of 5 comparing that same piece to the whole rather than just to the other piece. We're going to look at that a lot in the next section of the course when we talk about a dilution. A dilution is going to talk about comparing a part to a whole. For example, if we have a 1 in 5 dilution, that's going to compare the parts of medication to parts of the total solution. So that is a 1 to 5, 1 part medication in every 5 parts of total solution. Now there's only 2 ingredients in a dilution. There's the medication, and then there is that water. So if I wanted to know the parts of medication to water, it's going to be similar to what we did up above. We still have only 1 part medication, but if we have 5 total parts of solution, and one of those parts is medication, 5 minus 1 is 4 parts water. So we can get that ratio out of that. Along with that, you might look at the ratio of water to total solution. Well, again, the total solution is 5 parts. If one of those 5 parts is medication, the other 4 parts is water. So you can see from that one ratio, that one dilution ratio of 1 in 5, I have 3 ratios that I can create from that. And depending on the situation and what I'm trying to calculate, any one of those 3 ratios may be used in a problem. Okay, let's look at, you guys, it looks like you have similar tables in your rooms to what I have here. I might have tables that are, the tables in my room here are 72 inches long and 18 inches wide. So the inches divide out, both 72 and 18 can be reduced by 18, give me 4 to 1. So here's another difference. Up above, we kept the ratio as an improper fraction. We didn't change it to a mixed number. Same thing here. Normally, if this were just a fraction, I would rate that as just 4. But since this is a ratio, I have to leave it as 4 to 1 because that ratio has to compare two numbers. Now, what you'll notice in all of the ratios we've made so far, here we compared inches to inches. Here we compared parts to parts. Up here, it was students to students. Every ratio we've done so far, we've compared two things that have the same label or the same units. In a ratio, that is a very important thing, is both numbers must have the same label, same units. So a ratio compares two things that are the same. So if I have 2 feet compared to 18 inches, that is not a ratio. Fortunately, I can change it, 2 feet, I can change it to 24 inches. So now it's 24 inches to 18 inches, and now it's a ratio. So the inches cancel out. Both 24 and 18 can divide by 6, so that's a 4 to 3 ratio. And again, I would not want to turn that into a mixed number. I'd want to leave it as a ratio. Now, a couple of things to point out here now. There are no units in my final ratio. Since the units of both numbers are the same, they always divide out and cancel out. So this 4 to 1 ratio, this is a length to width ratio here, has no units attached to it. Make that look a little bit more like a rectangle. So what that means is for every 1 unit of width, there is 4 units of length. And it doesn't matter what I use. If I measure the width in centimeters, there's going to be 4 times that many centimeters of length. If I measure the width in feet, there'll be 4 times that many feet of length. So the units no longer matter. I can go to whatever measurement system I want to with these ratios. Now there is something called a unit ratio. And there are some ratios out there that seem to always be expressed as unit ratios. A unit ratio means the denominator or the second number in the ratio is 1. So here, to turn that denominator into a 1, I would just divide by it. So I divide by 3, gives me 1 here. Now it gets a little awkward with this one because if I divide 4 by 3, I get 1 1/3. So I get 1 1/3 to 1 is my unit ratio. That one is not necessarily one that would make sense to turn into a unit ratio. But in medicine, we have drop factors. Drop factors are always expressed as out of 1 unit. We're going to look at those a little bit more in just a second. Let's see, what else would we have? If we got into mechanics, there are a lot of ratios, gear ratios and stuff like that would be expressed as a unit ratio. The one I can think of right now, the big one would be a compression ratio. In a compression ratio, it's your expanded volume compared to your compressed volume. So let's say your expanded volume is 510 cubic centimeters, and your compressed volume is 6 cubic centimeters, or 60 cubic centimeters. Well, the cubic centimeters divide out. We have our 510 over 60 that we need to reduce. Both of those can divide by 30, which would leave us with 17 to 2, which that is the simplest ratio we can create there. But compression ratios are usually expressed as a unit ratio. So to turn that into a unit ratio, I do have to divide both numbers by the denominator. So I divide by 2 makes that a 1. Divide the 17 by 2 makes that 8.5. So that's an 8.5 to 1 compression ratio. Well, what if we have two numbers that don't have the same labels? And we can't make them have the same labels. Let's say we go on a road trip and we travel 365 miles in 7 hours. There is no way that I can turn miles into hours or hours into miles. So this is not a ratio. This is what we call a rate. So that's the first big difference between a rate and a ratio. Is a rate compares two things that have different units, and a ratio must compare two things that are the same. The second is, well, most ratios are just left as common ratios, and only a few of them are converted into that unit ratio like we saw with the compression ratio. When we're dealing with rates, almost all of them are converted into unit rates. So for this one, I would have to divide out by 7 in the denominator to turn that into a 1. So 7 hours divided by 7 is 1 hour. There's my unit in the denominator. 365 miles divided by 7 is 52.142857143 approximately miles. So now we have that down to a unit rate. The bottom number, the second number in my ratio or rate, is 1. It's 1 hour, but it's still 1. It's a single unit. So most of the time we would write this without the fraction notation like this. So I'm going to round that to 52.14. And a lot of times when we're dealing with rates, that appearance of the fraction gets pushed off or hidden in the units. So you can see the fraction only appears in the units of that rate. In fact, there are a lot of times where the fraction appearance gets hidden altogether. For example, let's say on that trip, our car gets 24 mpg. Can somebody tell me what mpg stands for? Somebody is saying it there. Miles per gallon. Good. When we see 24 mpg, we need to be thinking this, 24 miles per 1 gallon. Because this is the form that we're going to need it in order to do any calculations with it. So there are rates and ratios all around us. Since we're dealing with rates right now, let's stick with rates. You know, we had miles per hour for speed of a car, miles per gallon for gas consumption. One that's going to be very common, almost all of you will see this at some point in your life if you haven't already. You might get a job where you're getting paid $12 per hour. That is a rate. You know, if you have let's say you work 30 hours and your gross pay is $330. Your rate of pay is $330 per 30 hours. So you have to convert that into a unit rate to get to your hourly wage. So you divide by the 30 on bottom to make that 1 hour. Divide by 30 on top to make that $11. So this example, 30 hours of work for $330 would be $11 per hour. Other rates that we would see. In medicine, we're going to have a lot of flow rates. So you may have a patient that is going to receive 4,000 milliliters of fluid over 8 hours. So that is 4,000 milliliters in 8 hours. We'll divide by the 8 hours. Divide by 8. Not necessarily hours, but just divide by the 8. Gives us 1 hour. 4,000 milliliters divided by 8 is 500 milliliters. So that is a flow rate of 500 milliliters per hour. Again, you notice that fraction gets hidden in the units. And we talked about drop factors. Drop factors actually fit in with the rates rather than ratios. A drop factor describes the thickness of a fluid. What a drop factor is the number of drops it takes to create a milliliter of fluid. And for IVs, we actually have to set the number of drops per minute that IV drips into, that the medication drips into the IV fluid that's going into the patient. So you might have a liquid that 25 drops, the abbreviation for drops is actually GTT, makes 2 milliliters of fluid. So our drop factor, or that rate is 25 drops in 2 milliliters, and we divide it out. Divide those by 2. We get 12.5 drops in 1 milliliter. So that's 12.5 drops per milliliter is that drop factor. Ratios are going to appear a lot in constituting our medications. We might have 120 milliliters of lidocaine in a 300 milliliter saline solution. Now it says saline solution, so solution implies it's the saline and the medication. So this is 120 milliliters out of a total of 300 milliliters. So the milliliters cancel out. Again, the units cancel out. So again, we're back to working with a ratio. And both the 120 and the 300 can be reduced by 60. So that is a 2 out of 5 ratio. So 2 out of every 5 units in that solution is lidocaine. So let's say we have a dilution. A dilution is, again, that ratio that we have a 1 in 8 dilution. So what that is saying is 1 part of medication. I'm going to use the generic word serum. Serum, as we mentioned before, can either refer to the medication or the concentrated solution. And the 8, it refers to the parts of total solution. We might ask, how much medication is needed to create 120 milliliters of solution? Well, that 120 milliliters is of the total solution, so that goes with the total solution. That would be the 8 on the bottom. Now I'm going to put my units in there. That's 120 milliliters. What that means, remember, in a ratio, both numbers must have the same units, so the top number must also be in milliliters. And now, just like we did with our percents, we can cross multiply. 1 times 120 is 120. And then we divide by the number on the other diagonal. So we divide by 8 is going to give us 15. You would put in 15 milliliters of medication to create 120 milliliters of solution. So you put in the 15 milliliters of medication and fill to 120 total, the rest being water. So we saw that process there. Let's say we have a 3 to 5, and we want to know how much is that going to be out of 35. To find that missing number, if I put in an x there, we've seen this process with our percents where we cross multiply. The two numbers that are diagonal with each other get multiplied. 3 times 35, which is 105. And then we divide by the number that's on the other diagonal with our variable. We divide it by 5 to get 21. So x is 21. That's a shortcut of a longer process. So back to our original proportion here, 3/5 equals x over 35. The longer process is that the diagonal products, those cross products, must be equal. So 3 times 5 is 105. We would multiply this way as well. 5 times x is 5x. Those two products must be equal. So we write the equation 5x equals 105. Well, we solve that equation by dividing by 5. X equals 21, which is the same answer we had up above. Because that equation always ends up being this number times x, and we solve that equation by dividing by the 5 in this case, we just came up with that shortcut of just cross multiply. Multiply these two numbers, and then instead of multiplying the other way, just divide by this one. Which works well when we have simple proportions like this, where x takes up that whole piece. The x is sitting up there all by itself. It's a little less accurate, less useful when we have something else with x. For example, we might have 4 over 3x equals 12 over 45. Here, x is not by itself. So we could cross multiply and divide, but we would still have to solve an equation. So here it's easier to just go ahead and cross multiply and create the equation. So on this diagonal, we have 4 times 45, which is 180. On this diagonal, 3x times 12 is 36x. So we get the equation 36x must equal 180. If we divide by 36, we get x equals 5. You could have done the cross multiply and divide thing here, but what you got to remember is it's not x that you're solving for, it's 3x. So if we cross multiply, 4 times 45 is 180, and then divide by 12, which would give us 15, you have to remember that is 3x equals 15. And then we'd still be solving the equation to get x equals 5. That type maybe wouldn't be so bad to cross multiply and divide and still solve an equation. But we run into ones like this. X minus 4 over 7 equals 10 over 35. So again, we could cross multiply and divide and set up another equation, but let's just go ahead and cross multiply. I'm going to do the diagonal that doesn't have a variable first. 7 times 10 is 70. This diagonal is going to be a little trickier. X minus 4 times 35. I'm going to do the 35 first. So 35 times x minus 4. So the equation I get there is that 70 equals 35 times x minus 4. And of course, we'd solve that. 35 times x is 35x. 35 times negative 4 is a negative 140. The 70 on the left side has not changed. What do we do next? Add the 140. Good. So 210 equals 35. And our last step is what? Divide by 35. So x equals 6. Now again, this is one where we could have cross multiplied and divided. We could have done 7 times 10 is 70 and then divided by the 35 to get 2. But you got to remember, x doesn't equal 2. It's x minus 4 equals 2. And then we'd still have to solve that by adding the 4 to get that x equals 6. So we would get the same result. It's just, I think it's, from what I've seen, students make less mistake if they just do the diagonal products. And there are some proportions where they have to cross multiply. For example, if you have a over 9 equals 4 over a. Let's make this a little easier. My a is kind of like 9. Let's say x over 9 equals 4 over x. There's no way to cross multiply and divide this. I have to do the cross products. So I do 4 times 9 is 36. X times x is x squared. So here we have x squared equals 36. So to solve it, we have to square root. So the squared, the opposite of squared is square root. So the square root of x squared gives us back x. Square root of 36 is 6. Or negative 6. Either one would actually make that proportion true. Now in real life, most of the time we're dealing with real life numbers here. Very few times does the negative 6 give us a valid answer for a real life situation. So now these proportions work with both our ratios and our rates. If we are driving, let's say we're driving at 60 miles per hour, and we want to know how long it's going to take to drive 540 miles. Now, many of you know you just divide this out to get a time, but we can set it up. 60 miles per hour is 60 miles per 1 hour. So putting it in that form now is going to help us calculate. On the other side, the 540 is miles, so that has to go on top with the 60. And we are looking for the hours. So that's what's going to be on bottom. So we cross multiply. 1 times 540 is 540. Divided by the 60 gives us 9. So it would take 9 hours to drive 540 miles. Or we might look at a drop. Let's say we have a solution that is constituted as 25 milligrams of medication in 4 milliliters of solution. And I want to know how much medication is in 50 milliliters. Well, again, I have that rate this time of 25 milligrams in 4 milliliters. On the other side, the 50 milliliters has to go with other milliliters, has to be on bottom. How much medication? So we will cross, of course, this is going to be milligrams. We will cross, multiply, and divide. 25 times 50 is 1,250. Divided by the 4 is what? 312.5. So 312.5 milligrams of medication in 50 milliliters of solution. We have to be careful with our ratios. We have to make sure that what we're looking at is what we want. So for example, if we are given a 2 in 7 ratio of serum to total solution, we might be asked how much water, how much sterile water is needed to create 140 milliliters of solution. Well, that 2:7 ratio here is of serum to total solution. Remember, serum is the medication. The 140 does represent the total solution, so that would fit. But are we looking for the amount of serum? And the answer is no. We're looking for the amount of water. How much water? Now, I could find it from this ratio here. I could do 2 times 40, or 2 times 140 is 280, divided by 7 is 40 milliliters. That's the amount of serum. And then I could find the total solution of 140 milliliters minus the 40 milliliters of the medication of the serum gives me 100 milliliters. That must be of water. So you have to make sure that what's in the ratio is describing both what you are given, in this case that was the solution, and what you're looking for. In this case, the other number was not what we were looking for, but we could use it to find what we were looking for. The other option here would have been we could create that ratio of water to total solution. In that ratio, the total solution would still be 7. If 2 out of those 7 parts are serum, how many parts have to be water? 7 minus 2 gives us 5. The other 5 parts would have to be water. So now in our ratio, the 140 is still total solution. Now when we cross multiply and divide here, 5 times 140 divided by 7 is 100 milliliters. That is the amount of water that needs to be put into that solution. The biggest thing we need to know with our ratios one thing that, as long as you make sure it happens, it'll avoid some very obvious mistakes, is the units that go here. Let's say this is milliliters. Then either this one or this one must also be milliliters. So if this one's milliliters, then these two have to be the same. If this is milligrams, this would have to be milligrams. Or that could be set up like this. This one's milliliters, then this one is also milliliters. Then both of these on bottom are milligrams. The relationship has to go one of those two ways. So back to this previous example here, we had a 5, well, let's just do a 2 and 7 relationship of serum in total solution. And we wanted to know the 140 milliliters of total solution. We could set that up in one of two ways. The way we did it was we had the 2 and 7, where the 2 represented the serum, and the 140 milliliters went here, and what we found was the 40 milliliters of serum here. So we had the same units here and here, and then these were both unitless. We could have, however, set it up with the 2 and 7 both on top like this. The 7 represents the total solution, so the 140 milliliters goes with that. And then we cross multiply and divide to get the 40 milliliters here. So you can see there the milliliters are like that. These are the exact same ratio, just set up differently. If this were a more formal class in college algebra or whatever, we would talk about exchanging the means and the extremes and whatever. The biggest thing is since these two numbers are going to get multiplied in our cross product, we can switch their location. Switching the 7 and the 40 doesn't change the result of that ratio. Okay, so for Friday, in your book on page 73, 1 through 39, the odds, goes through writing ratios, simplifying or reducing ratios, and then looking at some of these basic proportions and finding the missing numbers in those proportions. So we're back at full strength. It looks like our next, we don't have to worry about anybody being gone until I think like March 17th. So we should be able the next few weeks. Oops, go ahead.
I have a question.
Yeah.
What is our next test?
Your next test. Very good question. Let me look ahead here and see what we've got coming up. So we've got Friday's lecture is going to be applications of percents and interest. Next Monday, we'll be looking at exponents, scientific notation. It looks like next Wednesday is going to be your next test. So we're coming. Oh, well, just a second. Hold up. Let me. I got ahead of myself. It'll be the following Wednesday would be your next test. Sorry. So a week from next Wednesday. So 2 weeks from today would be your next test.
Okay. Thank you.
You bet.